Welcome to Hobby Electronics. This is episode number 63 in the category of microcontrollers. Overall, this is 192nd publication. This is presented by P. Ram. The topic of this week's episode is learning to write and read from 24C02 8-pin EEPROM using Arduino Uno. The objective of the present work. In general, a 7-segment bit pattern dynamically calculated in the code. This occupies RAM memory in the microcontroller. The 24C202 EEPROM allows storing them as a lookup table. This saves RAM and processing power in the microcontroller. The 24C02 has 256 bytes of memory. It has plenty of room to store bitmap sets. Libraries needed for 24C02 EEPROM. The Arduino Uno has internal EEPROM. The EEPROM.h library is specifically designed for the internal EEPROM of the Arduino microcontroller. This can be more or less used for 100 times. Beyond that, 100 times writing and erasing, it becomes redundant. This library cannot be directly used with external I2C EEPROM like 24C02. 24C02 EEPROM is an I2C device. The wire.h library needed to write to an external EEPROM using I2C communication. Pin diagram of DIP package of 24C02 EEPROM. Pin number 1 AD0. Pin number 2 AD1. Pin number 3 AD2. These 3 pins together decides the address of the I2C bus of the EEPROM in the circuit. Pin number 4 is the ground. Pin number 5 is the serial data. Pin number 6 is the serial clock. Pin number 7 is the write protect. Pin number 8 is the VCC, or power supply to the EEPROM. The wiring of Uno with 24C02 external EEPROM. First step, connect your 24C02 IC to Arduino Uno using the following steps. Step 1. Connect VCC pin 8 of EEPROM to Arduino 5V power supply. Step 2. Connect pin 4 ground of EEPROM to Arduino ground. Step 3. Connect SDA pin 5 of EEPROM to Arduino A4 pin. Step 4. Connect SCL pin 6 of EEPROM to Arduino pin A5. Step 6. connect A0, A1, A2 pin, that is pin number 1, 2, 3 of EEPROM to Arduino ground. This sets the I2C address to hex 50. Step 7. Connect write protect pin number 7 to Arduino ground. This disables write protection. The circuit diagram of EEPROM configuration configured to address 50H is given here. The Uno connection is given in subsequent slides. Steps to wire 240C02 EEPROM to Uno. Step 1. Connect A4 pin of Uno to pin 5 of 24C02 EEPROM. Step 2. Connect pin 5 of Uno to pin 6 of 24C02 EEPROM. Step 3. Connect plus 5 volt power line of Uno to pin 8 of 24C02 EEPROM. Step 4. Connect any ground pin of Uno to pin 4 of 24C02 EEPROM. Step 5. Pin 1, 2, 3 and 7 of EEPROM is connected to the ground. Step 6. Connect a 4.7K resistor one end to pin 5 of EEPROM and another end of the resistor to plus 5 volt. Step 7. Connect 4.7K resistor one end to pin 6 of EEPROM and another end of the resistor to plus 5 volt. The complete wiring diagram of 24C02 with Arduino Uno for writing and reading purposes is given in this page. This is the photograph of the testing bed developed in breadboard using Arduino Uno and 24C02 EEPROM. Why the pull-up resistor is needed? The I2C hardware design. The SDA and SCL pin on both Uno and 24C02 are having open drain circuit. This means they can only actively pull the line down to the ground low. They cannot push the line up to 5 volt, that is high logic. How to fix? An external 4.7K resistor constantly pulls the line up to 5 volt. When the chip wants to talk, they will pull the line down. Without them, the line float in an undefined state and Arduino reads them as 0. This will lead to error in reading and writing. The CPP code for scanning the I2C bus for device connected and identification of the device address is given in this episode, in this section. The CPP code given here is the library inclusion and the setup of the environment. This is the loop section which repeatedly executes the loop it starts with the device address 0 and scans the I2C bus up to 128 address. And if a device is found, the success message is flashed and the loop repeats once in 3 seconds. One can type in the code in the Arduino IDE and or can request the author to for the entire Arduino file and start executing the scanning. The code with the IDE is given with the execution. Before running the code, open the serial monitor, set the serial monitor to 9600 baud rate. The scanning result will be displayed in the serial monitor. One can see the device address connected in my circuit. It flashes the device address as 50H. Working of I2C scanner code. This code scans the I2C communication bus to find connected hardware address. It pings every possible address from 1 to 128 and checks for the response. The core mechanism and method of scanning. The script exploits the feature of I2C protocol. When a master device pings a valid address, that device must send back acknowledgement signal. The wire begin address prepares the data packet targeted at the specific address. The wire end transmission sends the packet and return a status code based on whether the device acknowledged it. Line by line code execution breakdown. 1. Setup phase. The code in the section runs only once. Include wire.h. This line imports the standard Arduino library required for I2C communication. Wire.begin initiates the Arduino as I2C master device. Serial.begin 9600 opens the serial communication at 9600 bits per second to send text message to the computer screen, that is serial monitor. While not serial, passes the code execution till senior monitor window is actually opened. 2. The scanning loop repeats continuously. For address 1 to address less than 127, address plus plus, the standard I2C uses 7-bit addressing, creating a range of 1 to 127. Address 0 is reserved for broadcast message, so the loop skips it. Next, error is equal to wire end transmission. This is the heart of the scanner. It captures the response code from the bus. 0 for success. If a device exists in the I2C bus for that address generated in the for loop, an acknowledgement is sent. 4. Unknown error. Something is connected but misbehaving. Example, a short circuit or a line noise. The error 4 number message is flashed by the connected device. Other codes like 2 or 3, no device response at all in that address. Formatting and printing. If address less than 60, serial print 0. This line adds a leading 0 to the number smaller than 16, hexadecimal 10. So the printed address is address format cleanly printed as two digit. Example 0F instead of 0 hex F. Serial.print address hex. This code converts the numerical address into standard hexadecimal format. Delay 5000. Pauses for 5 seconds to prevent the flooding of serial monitor with the text. Steps for identification of the fault in case the address is not displayed or an error device not found message is flashed in the serial monitor. Incorrect I2C communication. Start/stop conditions. Ensure correct I2C start and stop condition are generated. 2. Slave address. Verify the correct 7-bit slave address for 24C02 EEPROM, including the read-write bit. 3. Acknowledge. If the EEPROM acknowledges the slave address and the data byte, a NAC indicate a communication issue. 4. Data format. Ensure data is transmitted and received in the correct byte order and format. Hardware connection. Pull-up resistors. Ensure appropriate pull-up resistors are connected to the SDA-SCL line. A typical value of 4.7K for 5-volt system is used. One can work around with 10K resistors also. Wiring errors. Double check all the connection between the microcontroller and the 24C02 for loose connection, short circuit or incorrect pin assignment. Solution. Visually inspect all the connections and use multimeter to check the continuity and for shorts. Check for specific chip version. Variation in chip exists. Always confirm the voltage for a chip you have by following these steps. Identify the manufacturer and the specific part number. Full part number may include suffix like -C or -R or other letters that indicate the voltage range. The manufacturer logo or name is often printed on the top of the chip. Look up the official data sheet. Use the full part number and find the manufacturer data sheet online. Websites like Octopart or All Data Sheet aggregate this information. Read the absolute maximum rating or DC electrical characteristic. This section of the data sheet will list the minimum and the maximum recommended supply voltage VCC for the safe, reliable operation. So, solution for troubleshooting. Review your I2C communication code or library function carefully. Compare them against 24C02 datasheet I2C protocol and specification. Use oscilloscope or logic analyzer to monitor the I2C line, SDA and SCL to observe the actual signal. Identify any discrepancies in wiring. We have set an objective of creating lookup table for 7-segment display. This display can display letters from 0 to 9 and A to F. This display has two types, common anode and common cathode. And there are two more options, that displaying with dot and without decimal point. So 4 lookup tables are created and organized in the memory of EEPROM. The mathematics and the memory map. Each character 0 to 9, A to F requires 16 bytes per set. Since you have 4 distinct sets, your total layout will look like as given below. Set 0, common cathode without decimal point, address from 00 to 0F. Set 1, common cathode with data point, address from hex 10 to 1F. Set 2, common anode, no data point, address from hex 20 to hex 2F. Set 3, common anode with dot point, address from 30 hex to 3F. The total byte space used is 64 bytes out of 256 bytes available. The purpose of creating a lookup table. The purpose of lookup table in this setup is to translate the raw binary BCD input into exact segment pattern needed to drive the 7-segment display. It replaces dedicated decoder chip by instantly mapping an input value to the correct LEDs. In this page, the example of bitmap saved in EEPROM for one unit, one set is given. The A is the least significant bit and dot point is the most significant bit, and the bits are arranged in such a way so that it will display numbers from 0 to F. See the table marked with the square. The CPP code to write lookup table of 7-segment display to 24C02 EEPROM. Procedure to use this code. Open Arduino IDE, paste this code and upload to your Uno. Open your serial monitor at 9600 baud rate to verify the terminal output, the final confirmation success lines. Once completed, 24C02 will retain the lookup table permanently, allowing you to run the read code provided anytime you boot up. This is the first page of the code. It captures the definition of variable, address, and the library included in the code. This is the second page of the code, wherein the setup is functions in the setup is captured. This is the third page of the code, and the setup function continues in this section page also. This is the loop section which executes repeatedly, and it is deliberately kept empty so that the data is written only once in the EEPROM, and the write sub-function is captured in the page number 4. Copy all the page code into Arduino IDE and compile and execute. The progress of compilation is captured in this page. The flashing of compiled code to Uno is captured in the page. This page shows the serial monitor output. After executing the code and writing each and every set, the successful writing is messaged out in the serial monitor. During this section, we are going to deal with the working of the C++ code to write into 24C02 EEPROM. 4 sets of data for 7-segment display lookup table is written using the code given. We will see this in the subsequent sections. Key technical details. A delay of 5 millisecond rule. External EEPROM hardware takes time to physically commit data to its transistors. Without 5 millisecond delay after every single end transmission, the data blocks will skip or get corrupted. Bit manipulation. The code avoids manual array typing by programmatically adding the dot point. By adding hex 80 and automatically mirroring the pattern to suit the common anode configuration. Working explained. Step 1. Initialization and setup. Wire begin initializes the I2C communication bus as a master device. Serial begin 9600 baud rate. Sets up serial communication at 9600 baud for debugging status messages. CC node 16 contains 16 hex values representing 7-segment display pattern for character 0 to F in common cathode configuration. Logic high turns on the segment. Second step. The data transmission and flashing loops. The setup function runs 4 consecutive loops to modify the base array and store 64 total bytes of data across distinct EEPROM memory sectors. Set 0. This is addressed from 0 to 15. Common cathode no decimal points. This set of address stores the common cathode no decimal point display pattern value into the first 16 memory bytes. Set 2 addresses 16 to 31. Common cathode with decimal point. Applies a bitwise OR operation on common cathode no decimal point, 80 hex value. This forces the most significant bit, usually representing the decimal point of the segment, to 1. Set number 2 addresses from 32 to 47. Common anode no decimal point. In this set of address applies a bitwise NOT operation on common cathode no decimal dot and stores the pattern. This inverts all the bits because common anode display require logic low to turn on the segment. Set number 3 address from 48 to 63. Common anode pattern with decimal point. Inverts the bit after turning the decimal point on. The common cathode no decimal point is added with 80 hexadecimal. This ensures the decimal point segment is correctly driven low for the common cathode display. I2C transmission mechanics to write EEPROM. The data is physically committed to hardware by using write EEPROM byte address and byte data function. Write dot begin transmission with the address of the device. This opens the I2C communication channel with the device at the address hex50, the standard hardware address for 24C02 EEPROM. The address can be changed to any value based on the wiring of A0, A1, A2 address pins of the EEPROM. Wire.write address sends specific internal memory location byte where the data should live. Wire.write data sends the transformed 7-segment byte to be written. Wire.end transmission stops the communication, prompting EEPROM to process the received data. Delay 5 halts the execution of the microcontroller for 5 milliseconds. This is critical hardware constraint. The 24C02 requires a self-timed physical write cycle time, typically of 5 milliseconds, before it can accept another write command. Fourth part of working, the completion. Serial.println flashing complete confirms all 64 bytes are successfully written. Void loop stays completely empty, ensuring program does not execute or do nothing after setup and prevents rewriting of EEPROM repeatedly. And from this section, we are going to deal with the reading of data from 24C02 EEPROM. Components needed: 7-segment common anode or common cathode display 1 number, Arduino Uno, data written EEPROM 24C02 1 number, jumper wires, 390 ohm resistor quarter watt 8 numbers, and breadboard. We are looking at the pin diagram of the 7-segment display. 7-segment display is of 2 types. One is common anode, another is common cathode, and the pin count starts from the lower bottom left. Dot point is an indicator of keeping the bottom of the display, and pin numbers are given against each red dot. The wiring of 7-segment display with Uno is given. 7-segment display pin number is in the first column. Label of that pin is in the second column, and the fourth column shows the Arduino pin connection. It is advisable to use 390 ohms resistor in each and every segment. For testing purposes, I have used only one 390 ohms in the common point. Circuit diagram for reading the EEPROM bitmap and displaying the value in the 7-segment display is given in the next page. This is the wiring of the actual circuit diagram. The IC24C02 connection with Uno is same as that of the writing circuit given previously. Additionally, the 7-segment display is connected on the right hand side of the Uno. Pin number 2 to A segment and pin number 10 to the G segment. The order is followed from 2 to 9. A 390 ohm resistor is connected to the common ground. A 10K resistor is connected to the common point and the ground pin of the Uno. Pin number 10 is used for auto detecting in the display type. The common cathode or common anode type is automatically detected by the software, and accordingly the bitmap is displayed in the 7-segment display. The actual photograph of the working test bed is given in this page with full assembly. Note on pin 7 of IC24C02. Connect the pin 7 of 24C02 EEPROM to the ground to read data from it. Connecting it to the ground is a standard practice for normal read and write operations. Pin 7 functionality explained. On a standard 24C02 EEPROM, pin 7 is a write protect pin. Connecting to the ground low. Write protect feature is disabled. One can both read from it and write to it the entire memory bank. Pin 7 of the 24C02 connection to VCC. Connecting to VCC high. Write protection feature enabled. The memory becomes read only, protecting your data from being accidentally overwritten. What this means for your project. Because reading data is never restricted to write protection pin, you can successfully read EEPROM whether the pin is tied to the ground or VCC. However, keeping it tied to the ground is most common configuration during development because it allows Arduino microcontroller to update or initialize data on the chip whenever necessary. The automatic common anode or common cathode detection feature in the software is explained in this section. Overview of auto common anode common cathode detection. The Arduino can detect whether it is grounded or tied to VCC at startup. A single configuration sensing pin wired to your display common pin can do this job. It will then dynamically pull the correct setup from the 24C02 EEPROM and display. Displayed in two ways: randomized digit from 0 to 9 A to F or sequential digit from 0 to 9 A to F. The circuit setup for auto detection. An analog digital sensing pin number 10 of Arduino Uno, connected to the common pin of 7-segment display. This enabled automatic type detection using the code and send correct pattern of data to the display. Pin 10 of Arduino Uno connected to the common pin of 7-segment display. Display common pin to D10. Detection circuit requirement. Connect a 10 kilo ohm quarter watt pull down resistor from pin 10 of Arduino Uno to ground. display segments A, B, C, D, E, F, G and dot point connected to Arduino pins 2, 3, 4, 5, 6, 7, 8, 9 via current limiting resistor 330 ohm 1/4 watt. Working of the auto detection. If a common cathode display is plugged in, the common pin is naturally connected to the ground. Pin 10 stays low. If a common anode display is plugged in, the common pin naturally connected to VCC 5 volt. Pin 10 is pulled to high. The Arduino reads the state at the boot before turning the pin 10 into an output pin to power the display. Important notes on the implementation. Current limiting. You must use 390 ohms quarter watt resistor in series with the segment pin to prevent the Arduino 7 segment LED from burning and damaging the Arduino Uno. EEPROM pre-flash. If this code, for the code to work, you must have already burned the programmed the correct 7 segment binary mask. In the test bed, I have used 390 ohm resistor in the common point to minimize the wiring. This will have implication on the brightness of the display. As more segments are displayed, the brightness may fluctuate. Users are advised to use discrete 390 ohm resistor to the segment and the dot point. Method 1. The CPP code for auto detection and reading LUT table full into the MCU buffer and random display. This is the first page of the code where the variables and functions are initialized. This page contains the setup section of the CPP code where the pins and the sub-functions are defined and initialized, and the auto detection happens. This page contains the part of the loop section where the randomized decimal, non-decimal place is decided and the target address is set and the data is pulled in from the EEPROM IC. This 4-page code is copied into the Arduino IDE and compiled. The compiled version screen is posted in this page. Anyone who needs the code may contact for the INO file. This is the output generated in the serial monitor. It clearly shows the character displayed and the address mask of it. In this section, we are going to deal with the working of the C++ code to read data from I2C EEPROM and display data in 7-segment display with auto detection of the type of display. This process of display is done in random. Hence, this is tagged as method 1. Working overview. The Arduino Sketch is an intelligent system that reads pre-compiled 7-segment display pattern from the 24C02 IC EEPROM and flashes the random character 0 to F every second. The clever part of the code is that it automatically detects if you plug in a common cathode or common anode display. and dynamically pulls the correct map from the EEPROM. The core logic, how EEPROM is organized. The code assumes your 2402 EEPROM contains 4 distinct lookup table, LUT in short, in future it is called, stored sequentially. Each LUT takes up to 16 bytes, 1 byte for each character from 0 to F. Set 0, address from 0 to 15, common cathode, no dot point. Set 1, address from 16 to 31, common cathode with dot point. Set 2, address 32 to 47, common anode, no dot point. Set 3, address 48 to 63, common anode with dot point. The detailed working of the code is given as walkthrough. The setup phase and hardware auto detection. Random seed analog read A1. This reads the electrical noise from the unconnected analog pin. This ensures the random function generates a completely different sequence of character every time, and the Arduino boots. Auto detect block. It temporarily configures the common control pin number 10 of Uno as a internal pull-up resistor holding it at 5 volt. If a common cathode display is attached, its internal segment diode pull this pin down to ground. This code sets the detected type of display as common cathode and configures the pin 10 as the output sinking low. If common anode display is attached, pin 10 stays high. The code sets the detected type common anode and configures pin 10 as an output pushing to high. The main loop, which repeats the action. Every 1 second the code executes 3 steps. Step A, mathematical address mapping. Step B, fetching from I2C EEPROM. Step C, pushing the display hardware. The formula for mathematical computation of address is given below. Target address is equal to detected type multiplied by 2 plus dot state multiplied by 16 plus random character. Step A, mathematical address mapping. The code picks a random character from 0 to 15 and flips the virtual coin to decide if the decimal point should turn on or off dot state. It then calculates the exact address where the specific pattern lives inside the EEPROM using the formula given in the below. Example, if the hardware is common cathode and wants a number 3 to be displayed with decimal point. For common cathode, internal value assumed is 0 and the decimal point is stored after address 16, after the address 16. So set number 0 into 2 plus 1 is equal to 1. Target address 16 into 1 plus 3 is equal to 19. The address in EEPROM is 13 hex. Step B, fetching data from I2C EEPROM. Wire begin transmission with EEPROM address, wire write target address, wire.in transmission, wire.request from EEPROM address. This pings the memory chip, moves its internal memory pointer to the calculated address, and requests a single 8-byte segment pattern. Step C. Pushing to the display hardware. Once the byte arrives, wire.available is flagged. The code loops through all the 8 output pins. For int I is equal to 0 less than 8, I plus plus, loop, digital write segment pins, sets the pattern in the 7-segment display. The working images presented in this page shows the random display of the character pulled for common cathode. The working of random value and random dot point is displayed in the page. This is the continuation of the random display. The working image is captured and posted in this page. Random number display and the random dot point selection is shown in this page as example using the test bed circuit. This section describes the second method of CPP code to read from the EEPROM. The CPP code for auto deduction and sequential display is given in this section. This code is for the common cathode. This is the wiring of the actual circuit diagram. The IC24C02 connection with Uno is same as that of the writing circuit given previously. Additionally, the 7-segment display is connected on the right hand side of the Uno. Pin number 2 to A segment and pin number 10 to the G segment. The order is followed from 2 to 9. A 390 ohm resistor is connected to the common ground. A 10K resistor is connected to the common point and the ground pin of the Uno. Pin number 10 is used for auto detecting in the display type. The common cathode or common anode type is automatically detected by the software, and accordingly the bitmap is displayed in the 7-segment display. The sequential access of data from 24C02 EEPROM and displaying is divided into 6 sections and presented in the 6 pages from here. The page 1 shows the library initialization and the variable and sub-function needed are initialized also. This is the second section of the code. This presents display detect type sub-function. This function is executed to detect the display type as common anode or common cathode. The page 3 shows the setup section. The wire begin initializes the I2C bus, serial begin initializes the serial monitor. The 8 pins of the segment which outputs the data is initialized, and a random seed for generating random number is initialized using analog, and detect display type function is called in this section. This is done only once during the execution of the code. This is the fourth page of the code. This contains code within the loop. This loop is repeatedly executed after a delay of 2 seconds. Here the data is loaded into the RAM. The address is sequentially generated. Every time the I2C bus seeks the data from the EEPROM for that particular address and sent to the display. Here the address is determined by the display type and the dot point. The page 5 portrays the subroutine get segment pattern. Here the address is transmitted to the I2C EEPROM and gets the data. Page 6 portrays the subroutine display digit. The pattern obtained from the EEPROM is sent to the 7-segment display for displaying the pattern in color. One can copy and paste all the code, 6-page code, into the Arduino IDE and compile and utilize. If anyone is in need of the code, please contact. In this section, the working of C++ code to read the data from I2C EEPROM in a sequential way and display data in SSD with auto deduction feature is explained. This is the explanation for method 2, sequential access of data. Working of the sequential access method 2 code overview. This is the Arduino sketch. Enables direct hardware interfacing. It automatically detects if a display is common anode or common cathode, reads the corresponding 7-segment digit pattern with or without a decimal point from 24C02 EEPROM. The Arduino Uno drives the segment pins sequentially. Section 1. Pin configuration and reduction. The segment pins. The code assigns pin number 2 to 9 to map the standard 7-segment layout A, B, C, D, E, F, G and the dot point. Auto detect. In setup, the detect display type function defines the common pin as the input pull-up. If it reads low, it generates common cathode. If it is high, it registers as a common anode and actively outputs the high to drive the display. Section 2. EEPROM addressing and read pattern stored. The 24C02 memory is organized into logical tables. The function getSegmentPattern translates your desired character and decimal display state into specific target memory address. I2C transmission. It uses standard Arduino wire library to transmit the address byte and request 1 byte of data back to use as a binary pattern mask for the segment LED. The display execution. Display digit subroutine. The display digit byte pattern function bit reads the mask received from the EEPROM. If the bit is 1, it turns the corresponding segment pin to high. If it is 0, it turns off. And this results in the display of the sequential number in the 7-segment display. The serial monitor output. While code executing, the serial monitor gives the status of which data is accessed and the mask of the data. Here you can see the sequential progression from A to F when the screen is captured. The sequential display of the pattern pulled out from the EEPROM 24C02 is shown in these images. The images are captured from the working circuit. This is the continuation of the working of the sequential display, and this page displays the pattern display from 8 to hexadecimal F. Comparison of sequential and random method of processing the EEPROM data and displaying. Comparing the random method, the method 1, with that of the sequential, method 2. Feature I2C activity. Method 1 fires only once inside the setup. Method 2 fires every single second inside the loop. Feature speed. Method 1 microseconds. It is instant internal RAM speed. Method 2 slow 1 to 2 millisecond lag to open the bus and request data. Power consumption. Method 1 direct address read. Random method. Lower power consumption because bus stays idle after boot. Higher power consumption is needed in the method 2 as I2C bus toggles continuously. RAM overhead. Method 1, which is random, consumes 64 bytes of Arduino RAM. Method 2 uses 0 byte of Arduino RAM. Application of random display method. In our case, method 1 in coding. Gaming and gambling devices. Digital dice, random number generator or electronic slot machine use random number display. Testing and quality assurance. Bench testing 7-segment displays for burn-in or verifying that all data sectors inside a newly flashed EEPROM are reachable. In this case also, random display method is used. Applications of sequential display method of coding. That is in our category, it is method 2. Industrial dashboard and instrumentation. Digital clock, countdown timers, manufacturing tally counters, and queuing system displays use sequential display method. Automotive telemetry. Digital speedometers, gear indicators, or tachometers where data flows sequentially and updates must happen at a high refresh rate without flickering. The method 2 sequential is used. A good practice in compiling. This is for those who are using Arduino IDE environment in Windows 10. In case of entering a strange, inexplicable compilation error, follow the steps given below. Go to sketch, verify/compile, or press Ctrl plus R/Command+R. If persists, simply close the IDE completely and reopen it. This forces the build environment and usually clears up any ghost errors. In general, in a developing stage of a project, sequential testing is done to remove all the execution errors. Reason for sequential testing: when building a project with I2C EEPROM and 7-segment displays, switching from random to sequential processing is actually the best way to verify everything works correctly. Hardware verification. A sequential loop of 0 to F lets you to visually check if every single segment A to G and the dot point lights up properly. If you rely only on random numbers, it might take long time to see E, R and F, making it harder to spot broken wire or a faulty segment. Database validation. It confirms that your EEPROM flashed correctly. By watching the display counting up in a perfect order, you prove that the address calculation mathematics matches that of the exact memory slot where the data pattern is saved. We have seen so far two methods of reading the data. Method 1 is the random, which pulls up the entire EEPROM data to the built-in buffer in the microcontroller and executes the code in random way. The method 2 is the direct access and getting the data every time information is needed. So the method 2 is much better for the sequential test. Sequential read data done. Reasons for method 2 preferred choice is specifically to verify the hardware and testing the code. 1. True live hardware testing. Method 1 copies everything to the RAM once at boot. If I2C wires disconnect or fail after initial boot, the sequential test will keep running perfectly from RAM, hiding the hardware failure from you. Method 2 talks to the physical EEPROM chip every single loop of iteration. If there is a loose I2C wire or bad solder joint or faulty pull-up resistor, the display will fail or freeze immediately. This gives you instant diagnostic feedback. The second advantage of the sequential recollecting of data from EEPROM is it is a perfect process to spot the memory corruption. If you made an error in flashing code, method 2 allows you to see exactly which memory address is corrupted as the counter processes it. Because it is directly linked to the counter variable n to the physical memory location in real time, it acts as a direct window to EEPROM chip. Third advantage of the sequential test: no RAM is wasted. Method 2 uses 0 byte of the internal microcontroller ROM for a simple test bench where you just want to verify that the segment A to G light up in an order. There is no need to consume 64 byte of precious RAM memory to catch data. Preferred method for working. Method 1 is preferred. Method 1 is for the random access. You should only switch to method 1 after sequential test passes all the criteria and you move to the final project execution, especially if you need to update the display hundreds of times per second, or you want to eliminate I2C bus traffic to save the power during the battery operation. Conclusion. 24C02 EEPROM can be used to store LUT. This is the fast and efficient way in microcontrollers where resources are less. The cost of the kit for this project is approximately 550 rupees with GST, packing and courier extra. In case of need, please contact the channel owner for tips, support, assistance, guidance and free code distribution. Kits are available for learning electronics in a hobby way. Projects for schools and college work can be designed. Contact the YouTube owner. Subscribe to my YouTube channel. Follow the link to my YouTube channel. Thanks for watching. This is the end of this session. Bye.